Hello everyone, my name is Abhishek and today's my topic is motion in a magnetic field. In this topic, we are going to understand how charged particles move in an applied magnetic field. So here we take two cases. First, when charged particle is moving perpendicular to the applied magnetic field, and in second case when charged particle making some other angle than 90. So for first case, suppose that magnetic field is going inside the whiteboard like this, and charged particle is moving perpendicular to the applied magnetic field. So suppose somehow charged particle reaches here in magnetic field and it tries to move perpendicular to the applied magnetic field. Then whenever there is a charged particle moving in a magnetic field, there is a magnetic force which is equal to Q V cross B. So, and the direction of force is given by Fleming's left hand rule. In Fleming's left hand rule, thumb shows the direction of force, first finger shows the direction of applied magnetic field, and magnetic field, and second finger shows the direction of motion of charged particle. So here the magnetic field is inside the whiteboard, charge tries to move in left hand side, and then force is in upward direction. So charged particle moves something like this. Here it reaches and it tries to move in upward direction. Again, there is magnetic force which is in. So, from Fleming's left hand rule, we can find the direction of again magnetic force. So, the charge magnetic field is in inside the whiteboard. Motion of charged particle is upward. So, force is in right side. So, charged particle moves something like this. Again. Fleming's left hand rule, magnetic field, motion of charged particle like this. So force is in downward direction. So charge will move here. Again, magnetic field like this, and velocity is in downward direction. So force is left hand side. So charged particle reaches here, and we see that charged particle moves in a circular path whenever velocity and magnetic field are perpendicular to each other. So, if velocity and magnetic field is perpendicular, then Q V B sine 90. So, magnetic force is equal to Q V B. As you can see, the charged particle is moving in circular path, then there arises centripetal force, and centripetal force arises due to the magnetic force. So Fc is equal to Fm. As we know, centripetal force is mv square by r, which is equal to qvb. Then radius of charged particle is mv by qv. If we take that magnetic field is constant, then we can see that mass of charged particle is constant. Suppose that the charged particle q is electron, then mass of the charged particle is constant, 9.11 10 to the power minus 31 kg, charge 1.6 10 to the power minus 19, and magnetic field is constant. So radius only depends on the velocity of charged particle. If velocity is high, then radius is large. If velocity is low, then radius is low. So this is the first point. And we know that V is equal to R omega in scalar form, or in vector form, which is omega cross R. So V is equal to R omega. So V is mv by qb, which is equal to R. Omega means 2 pi nu. So sorry. Not V R is equal to mv by qv. So V and V cancel each other. So we get qb by 2 pi m, which is equal to frequency. Here the main things is gonna happen. So radius is depends only on velocity, and frequency is constant. As here we have taken magnetic field constant, so q constant, b constant, mass of charged particle is also constant, which means frequency is constant. And as we know that frequency is 1 by t, which is equal to qb by 2 pi m. So t is equal to 2 pi m by qb, which means that time period is also constant. That means that if radius is large, then time period is t. If radius is small, then also time period is t. That means time period does not have any relation with the radius. It is always constant. If velocity is high, then radius is large. Then suppose that time period is 1 second. That charged particle moves in a 1 second. Takes complete one cycle in 1 second. If velocity is low, then radius is low. But again, time period is constant, which means that it again complete one cycle in 1 second. It does not have any relation with velocity or with radius. It always complete the cycle in same time. And now we are going to understand the second case in which the charged particle is moving with some angle other than 90. So suppose that magnetic field is something, here we have axis x, y, z, and magnetic field is in x direction, something like this. Okay. So if charged particle moving with some velocity v, which is making angle theta, so there will be two components. One is perpendicular component and one is parallel component. Parallel, which is parallel to the applied magnetic field. So as you can see here, that perpendicular component tries to move charged particle in a circular path. So this component try to move charged particle in a circular path, but this parallel component drags charged particle in forward direction. So charged particle move something like this. So, and this path is known as helical path. So when charged particle is moving other than 90, then it takes helical path. And here one component is important, which is known as pitch, which is distance between two peaks. So pitch is distance, and this distance is arises due to parallel component of velocity. As you know, velocity is distance upon time. Here distance is pitch and time is t, because from this peak to this peak, it takes time t, which is time period. One taking time to revolve one time. So pitch is something like v parallel into t, and as we know that t is 2 pi m by qv. So distance between the two peaks is v parallel 2 pi m by qv. So this is the charge. This topic is motion in a magnetic field, and if any query, then drop simple message. I will try to explain again. Thank you.